take a slow breath in and let it out gently. You don't need to do anything right now. There's nowhere you need to be, nothing you need to remember. Just let yourself settle into this moment, feeling the weight of your body wherever you're resting. Everything can wait. Everything is okay. Tonight, we're going to talk about space and time, but not in any complicated way, just soft thoughts about the universe around us, things that are happening far away, slowly, quietly, things that have been happening for a very long time. You don't need to follow every word. You can just let the sounds wash over you like gentle waves. Space is big. That's really the simplest way to say it. When we look up at the night sky, we see stars, and those stars are far away, much farther than our minds can really picture. But that distance is part of what makes the universe feel so calm. Everything out there is moving slowly from our perspective, changing over millions and billions of years. There's no rush. There never has been. Light travels fast, but space is so large that even light takes time to cross it. When you see a star in the sky, you're seeing light that left that star years ago, sometimes hundreds of years ago, sometimes thousands. The light has been traveling through empty space all that time, moving toward us, and finally it reaches your eyes. You're seeing the past, not your past, but the star's past. A gentle reminder that time and distance are connected in ways that feel almost like a dream. Our sun is a star, too. It's close to us, relatively speaking. The light from the sun takes about 8 minutes to reach Earth. So when you feel warmth on your skin from sunlight, that warmth began its journey 8 minutes earlier. It crossed the empty space between the sun and Earth, moving at the speed of light, which is very fast, and then it touched you. 8 minutes is not very long. You could walk around your neighborhood, make a cup of tea, listen to a song or two, and in that same time, light travels from the sun to here. But other stars are much farther away. The nearest star to our sun is called Proxima Centauri. It's a small, dim star, and the light from it takes a little over 4 years to reach us. 4 years. So if you look at Proxima Centauri tonight, you're seeing what it looked like 4 years ago. If something changed about that star last week, we won't know for another 4 years. The universe has built-in delays. Information moves at the speed of light and no faster, so everything we see in the sky is a memory. This creates something gentle and quiet in the way we experience the universe. We're always looking at the past, always seeing things as they were, not as they are right now. And because space is so vast, those delays get longer and longer the farther out we look. Some of the stars you can see with your eyes are hundreds of light years away. Their light has been traveling for hundreds of years. Some of them may not even exist anymore. They may have grown old and faded, or changed in some way, but we won't know until their new light reaches us. There's something calming about that. The universe doesn't demand that we know everything right now. It unfolds slowly. It reveals itself to us bit by bit as light crosses the distances between things. Our galaxy, the Milky Way, is a collection of stars, hundreds of billions of them, all held together by gravity, all orbiting slowly around a common center. The galaxy is shaped like a flat disk with a bulge in the middle, and our sun is located out in one of the spiral arms, about halfway from the center to the edge. We're in a quiet part of the galaxy, not too crowded, not too empty, just a calm spot where a star like our sun can exist for billions of years without much disturbance. The Milky Way is big. If you tried to cross it at the speed of light, it would take you about 100,000 years. 100,000 years of traveling as fast as anything can travel, and you still wouldn't have crossed from one side to the other. But you don't need to cross it. You're here on Earth, and that's enough. The galaxy is doing its slow rotation, and we're doing ours, and everything is moving together in a way that feels almost like stillness because the motion is so smooth and so constant. At the center of our galaxy, there's a supermassive black hole. It's very large, millions of times the mass of our sun, but it's also very far away from us, about 26,000 light years away, so we don't need to worry about it. It's just sitting there, quietly, holding the inner part of the galaxy together with its gravity. Black holes sound dramatic, but they're really just objects with a lot of mass compressed into a small space. They pull on things with gravity, just like stars and planets do. They're part of the natural structure of the universe. Around our galaxy, there are other galaxies, lots of them, billions of them. They're spread out across space in a pattern that almost looks random, but there's structure to it. Galaxies tend to cluster together in groups and clusters, and those clusters connect to each other in long filaments, like a web. Between the filaments, there are vast, empty regions called voids, where very few galaxies exist. The universe has texture to it, a kind of cosmic foam, with dense regions and empty regions all woven together. And all of these galaxies are moving, not just orbiting within their groups, but moving away from each other. Space itself is expanding. This is one of the most interesting things we've learned about the universe, and it happened less than 100 years ago. Before that, people thought the universe was static, unchanging, but observations showed that distant galaxies are moving away from us, and the farther away they are, the faster they seem to be moving. This isn't because the galaxies themselves are flying through space. It's because the space between them is stretching, like the surface of a balloon being inflated. As space expands, galaxies get carried along with it, moving apart from each other. This expansion is happening everywhere, all at once. It's not that we're at the center of the expansion. Every galaxy sees every other galaxy moving away. If you were in a distant galaxy looking back at us, you'd see the Milky Way moving away from you, just as we see that distant galaxy moving away from us. There's no center to the expansion. It's happening uniformly, gently, throughout the entire universe. The expansion of space means that the universe was smaller in the past. If we imagine running time backward, galaxies would get closer and closer together. Space would shrink. Eventually, if you go back far enough, everything in the universe was compressed into a very small, very hot, very dense state. That early state is what we call the beginning of the universe as we know it, and it happened about 13.8 billion years ago. The universe has been expanding ever since, cooling down, spreading out, becoming the vast, calm place we see today. In those early moments, the universe was too hot for atoms to exist. There were only particles of matter and energy moving around in a dense soup. But as the universe expanded, it cooled. After about 3 minutes, it was cool enough for the simplest atoms to form: hydrogen and helium, the two lightest elements. These atoms spread out through space as the universe continued to expand. For a long time, hundreds of millions of years, the universe was dark. There were no stars yet, just hydrogen and helium gas drifting through expanding space. Then, slowly, gravity began to pull the gas together. Small clumps formed, and those clumps grew larger. Eventually, the gas became dense enough and hot enough in some places that nuclear reactions started. The first stars turned on, shining light into the darkness. These early stars were different from the stars we see today. They were made only of hydrogen and helium because those were the only elements that existed. They burned brightly and lived fast, and when they died, they created heavier elements in their cores: carbon, oxygen, iron, and many others. When those stars exploded, they scattered those new elements into space, and the next generation of stars formed from gas that included those heavier elements. This process repeated over and over for billions of years. Stars formed, lived, died, and enriched the gas around them. Galaxies formed from collections of stars and gas. Planets formed from the material around some stars. And eventually, on at least one planet, life appeared. That planet is Earth, and that life includes us. So when you look at the atoms in your body, the carbon, the oxygen, the calcium, the iron, you're looking at material that was made inside stars billions of years ago. Those stars lived and died long before the sun existed. They scattered their atoms into space, and those atoms eventually became part of the gas cloud that collapsed to form our solar system. Some of those atoms ended up in the Earth, and some of them ended up in you. You're made of stardust. That's not poetry. It's just a description of where the elements in your body came from. Time is hard to imagine when we talk about billions of years. A billion is 1,000 million. If you counted one number every second, it would take you about 32 years to count to 1 billion. And the universe has been around for 13.8 billion years. That's an almost impossible amount of time to hold in your mind. But you don't need to hold it. You can just let it sit there in the background as a reminder that the universe is old and patient and slow. Our sun is about 4.5 billion years old. It formed from a cloud of gas and dust that collapsed under its own gravity. As the cloud collapsed, it spun faster, flattening into a disk. Most of the material fell into the center and became the sun. The leftover material in the disk clumped together to form planets, moons, asteroids, and comets. Earth formed about 4.5 billion years ago around the same time as the sun. It started as a ball of molten rock, too hot for liquid water. But over time, it cooled. Water condensed on the surface, forming oceans. The atmosphere changed, and eventually conditions were right for life to begin. Life on Earth started simple, single-celled organisms living in the oceans. For billions of years, life stayed simple, but slowly it became more complex. Multicellular organisms appeared: plants, animals, fungi. Life spread across the planet, adapting to different environments, evolving into countless forms. Humans appeared very recently, only about 300,000 years ago. If the history of the universe were compressed into a single year, with the beginning happening on January 1st, humans would appear in the last few minutes before midnight on December 31st. We're very new. But even though we're new, we've been able to learn a lot about the universe. We've built tools to observe distant galaxies, to measure the age of stars, to understand the expansion of space. We've sent spacecraft to other planets. We've walked on the moon. We've looked deep into the past by observing the light from distant objects. And all of this has helped us understand our place in the universe. We live on a small planet orbiting an average star in the outskirts of a typical galaxy in a universe filled with billions of galaxies. From that perspective, we're very small, but we're also part of the universe. We're made of the same atoms as stars and planets. We follow the same physical laws. We're not separate from the cosmos. We're woven into it. If you're still listening, that's wonderful. But if you've drifted off, that's wonderful too. This is meant to be restful. I'm Elara, and you're listening to Late Night Science Channel, but really none of that matters right now. What matters is that you're comfortable and calm and letting your mind rest. Let's talk a little more about light, because light is how we see the universe. Everything we know about distant stars and galaxies comes from the light they send us. Light is a wave, or sometimes it behaves like a particle, but either way, it travels through space at a constant speed. That speed is about 300,000 kilometers per second. Nothing can go faster than light. When light travels through empty space, it doesn't slow down or speed up. It just keeps going at the same speed until it hits something. When light from a distant star reaches Earth, it enters our atmosphere, and some of it reaches the ground, and some of it reaches your eyes. Your eyes detect the light, and your brain interprets it as an image. That's how you see. But light doesn't just carry an image, it also carries information about where it came from. If we split light into its different colors, we can see patterns that tell us what the light passed through or what kind of object emitted it. Stars, for example, emit light in specific patterns based on the elements they contain. By looking at the colors in starlight, we can figure out what a star is made of, even though that star is light years away. We can also tell how hot the star is, how big it is, and how fast it's moving. When a star or galaxy is moving away from us, its light gets stretched out. The waves get longer, and longer waves appear more red. We call this redshift. The faster something is moving away, the more its light is redshifted. When we look at distant galaxies, we see that almost all of them are redshifted, which tells us they're moving away from us. And the farther away a galaxy is, the more redshifted its light is, which means it's moving away faster. This is how we know the universe is expanding. There's a limit to how far we can see, not because space ends, but because light takes time to travel, and the universe has only been around for a finite amount of time. The farthest light we can see is light that has been traveling toward us since very early in the universe's history. That light comes from a time when the universe was only a few 100,000 years old. Before that, the universe was too hot and dense for light to travel freely. It kept getting absorbed and re-emitted by particles, so it couldn't move in straight lines. But once the universe cooled enough, light could travel freely. That moment is called recombination, and the light from that time is still reaching us today. We call this light the cosmic microwave background. It comes from every direction in the sky, filling the universe. It's very faint, and it's been redshifted so much by the expansion of space that it's no longer visible light. It's microwave radiation, which is a kind of light with longer waves than our eyes can see. But we can detect it with instruments, and when we do, we see a faint glow that represents the universe as it was 13.8 billion years ago, just a few 100,000 years after the beginning. The cosmic microwave background is the oldest light we can see. It's the edge of the observable universe, not because there's nothing beyond it, but because light takes time to travel, and the universe has only been around for a finite amount of time. Whatever light existed before that moment couldn't travel freely, so it never reaches us as light, and whatever is beyond the observable universe is too far away for its light to have reached us yet. The observable universe is like a sphere around us, with us at the center, and the edge of that sphere is the farthest distance light could have traveled in the age of the universe. But the universe itself might be much larger than the observable part. It might even be infinite. We don't know. What we observe is just the part that's close enough for light to have reached us. Beyond that, there could be more galaxies, more stars, more space stretching on forever. Or maybe not. We can't see it, so we can't say for sure. There's something peaceful about that uncertainty. The universe holds mysteries, and that's okay.
We don't need to know everything. We can appreciate what we do know and let the rest remain unknown, at least for now. Space is mostly empty. When we think of the universe, we often think of stars and galaxies, but those are just tiny islands in a vast ocean of emptiness. Between stars, there's mostly vacuum, a few atoms here and there drifting through space, but mostly nothing. Between galaxies, there's even less. Space is empty, quiet, and dark. But that emptiness is part of what makes the universe stable. If space were crowded with matter, gravity would pull everything together very quickly. Stars would collide, galaxies would merge, and the universe would be a chaotic, violent place. But because space is so empty, things are spread out. Galaxies can exist for billions of years without much disturbance. Stars can shine steadily for billions of years. Planets can orbit peacefully. The emptiness gives everything room to exist. Even on Earth, we're mostly empty space. Atoms are mostly empty. The nucleus of an atom is tiny, and the electrons that orbit it are even smaller, and the space between them is huge compared to their size. So if an atom were the size of a football stadium, the nucleus would be like a marble in the center, and the electrons would be tiny dots orbiting somewhere in the stands. Everything in between is empty. So your body, which feels solid, is actually mostly empty space. The atoms are held together by forces, and those forces give the illusion of solidity. But the reality is that you're mostly nothing, just like the universe. That's not a sad thought, it's just interesting. We're made of mostly emptiness, held together by invisible forces, and somehow that creates something as complex and wonderful as a living person. The universe is full of these kinds of paradoxes, things that seem impossible but are true. Let's think for a moment about time. Time feels straightforward. It moves forward, from the past, through the present, into the future. We experience it as a flow, a river carrying us along. But time is more flexible than it seems. It can stretch and compress depending on how fast you're moving and how strong the gravity is around you. If you were moving very fast, close to the speed of light, time would pass more slowly for you than someone standing still. This isn't just a theory, it's been tested. Clocks on fast-moving spacecraft run slightly slower than clocks on Earth. The difference is tiny, but it's real. Time itself is bending, stretching depending on motion. Gravity also affects time. The stronger the gravity, the slower time passes. If you were standing near a black hole where gravity is extremely strong, time would pass much more slowly for you than someone far away from the black hole. You might experience a few minutes, but to the distant observer, hours or days might pass. Time is not universal, it's personal, local, dependent on where you are and how you're moving. This means that the idea of now is not as simple as it seems. There's no universal now that applies to the entire universe. If you're on Earth and someone is on a distant star, moving at a different speed, your now and their now are different. You might think something is happening right now on that distant star, but from your perspective, what you see is that star's past. And from their perspective, what they see of Earth is also the past. There's no way to synchronize the two perfectly. Time is woven into space, creating something called spacetime, and spacetime is flexible, curved by mass and energy.
This is what Einstein figured out about 100 years ago. His theory of general relativity describes how gravity works by curving space-time. Massive objects, like stars and planets, create curves in space-time, and other objects follow those curves. We call it gravity, but really it's just the shape of space-time guiding things along certain paths. The Earth orbits the Sun not because the Sun pulls on it with some invisible force, but because the Sun curves space-time, and the Earth follows that curve. It's a strange way to think about the universe, but it matches what we observe. Light bends around massive objects. Time passes at different rates in different places. Space and time are connected, flexible, and shaped by the presence of matter and energy. All of this might sound complicated, but the feeling it gives is actually very calm. The universe follows rules. Those rules are sometimes surprising, sometimes strange, but they're consistent. Things behave the way they do because of the structure of space-time, the properties of matter and energy, the laws of physics. There's an order to it all, even if that order is sometimes hard to see. Galaxies aren't just scattered randomly through space. They're organized into clusters and superclusters, connected by filaments of gas and dark matter. Dark matter is something we can't see directly, but we know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by just the visible matter in them. There must be more mass we can't see, providing the extra gravity. We call it dark matter because it doesn't emit light. It doesn't interact with light at all, as far as we can tell. It just exists, invisibly, holding galaxies together, shaping the structure of the universe. Most of the matter in the universe is dark matter. The stars, planets, gas, and dust that we can see make up only a small fraction of the total mass. The rest is dark, hidden, known only by its gravitational influence. It's another mystery, a quiet one, sitting in the background of everything we observe. There's also dark energy, which is even more mysterious. Dark energy is something that fills empty space and pushes space apart. It's causing the expansion of the universe to accelerate. Not only is the universe expanding, but that expansion is getting faster over time. This was discovered about 25 years ago, and it surprised everyone. The expectation was that gravity would slow down the expansion, but instead it's speeding up. We don't know what dark energy is. We don't know why it exists or how it works. We just know that it's there, affecting the expansion of space. It's the dominant form of energy in the universe, making up about 70% of the total energy. Dark matter makes up about 25%, and everything we can see, all the stars and galaxies and planets, makes up less than 5%. Most of the universe is invisible to us. That's a humbling thought. We're living in a universe where most of what exists is hidden, but it's also a reminder that there's still so much to learn, so much we don't understand, and that's okay. The universe doesn't need to reveal all its secrets at once. It can take its time. Let's think about the Milky Way for a moment again. Our galaxy is part of something called the local sheet, which is a flattened group of galaxies that includes the local group. The local sheet is part of a larger structure called the Virgo supercluster, which contains thousands of galaxies spread out over millions of light years. And the Virgo supercluster is part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies. Laniakea means immense heaven in Hawaiian, and it's a good name. The structure is vast, almost incomprehensibly large, and yet it's just one small part of the universe.
There are countless other superclusters scattered throughout space, each containing thousands or hundreds of thousands of galaxies, and between them are the voids, enormous empty regions where very few galaxies exist. The cosmic web, as it's sometimes called, is the largest structure we know of in the universe. It's a network of filaments and clusters, with voids in between, and it stretches as far as we can see. This structure formed over billions of years as gravity pulled matter together in some regions and left other regions empty. It's the natural result of tiny variations in the density of matter in the early universe, amplified over time by gravity. If you could see the entire observable universe at once, you'd see this web, a delicate, intricate pattern of light and dark, with galaxies shining like tiny jewels along the threads of the web and vast, empty spaces in between. It's beautiful, in a quiet, understated way, not flashy or dramatic, just the natural structure that emerges when you let gravity work on matter for billions of years. Our sun will not last forever. Nothing does. Stars have lifespans, just like living things, though their lifespans are measured in billions of years rather than decades. Our sun is middle-aged right now. It's been shining for about 4.5 billion years, and it will continue to shine for another 5 billion years. That's a very long time, long enough that we don't need to worry about it. But eventually, the sun will change. Right now, the sun is fusing hydrogen into helium in its core. That's what makes it shine. The energy from that fusion pushes outward, balancing the gravity that tries to pull the sun inward. But eventually, the hydrogen in the core will run out. When that happens, the core will start to collapse under its own gravity. As it collapses, it will heat up, and the outer layers of the sun will expand. The sun will become what's called a red giant. When the sun becomes a red giant, it will grow much larger. It might expand far enough to swallow Mercury and Venus. It might even reach Earth's orbit, though Earth itself might have already drifted outward by then, because the sun will be losing mass and its gravitational pull will weaken. Either way, Earth will not be a comfortable place when the sun becomes a red giant. The heat will be intense. The oceans will boil away. The atmosphere will be stripped off. Life, if any still exists, will have to find somewhere else to go. But for now, the sun is stable, shining steadily, providing warmth and light to Earth, and it will continue to do so for a very long time. After the red giant phase, the sun will shed its outer layers. Those layers will drift off into space, forming what's called a planetary nebula. It's a misleading name because it has nothing to do with planets. It's just a cloud of gas, glowing in the light of the sun's exposed core. That core will be very hot and very small, no longer fusing anything, just radiating away its remaining heat. We call such an object a white dwarf. The white dwarf that used to be our sun will sit there cooling down slowly over trillions of years. It will fade from white to yellow to red to eventually black, becoming a cold, dark cinder floating through space. But even that takes an incredibly long time. The universe isn't old enough yet for any white dwarf to have cooled all the way to black. The oldest white dwarfs are still glowing faintly. Other stars have different fates, depending on their mass. Stars much more massive than the sun live faster and die more dramatically. They burn through their fuel quickly, sometimes in just a few million years. When they run out of fuel, their cores collapse suddenly, and the outer layers explode in what's called a supernova. For a brief time, a supernova can outshine an entire galaxy. It's one of the most energetic events in the universe. The core that's left behind after a supernova can become a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Or, if the core is massive enough, it can collapse further and become a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape from it. The boundary around a black hole, beyond which nothing can escape, is called the event horizon. Once something crosses the event horizon, it's gone. It can't come back. Black holes sound frightening, but they're really just very dense objects with strong gravity. They don't roam around sucking things in. They just sit where they are, pulling on nearby objects with gravity, just like any massive object would. If you replaced the sun with a black hole of the same mass, the planets would continue to orbit just as they do now. The gravity wouldn't change. The only difference would be that there'd be no light or heat. Neutron stars and black holes are the remnants of massive stars, the final stage of their existence. They're quiet, dark, and incredibly dense. Some neutron stars spin very fast, emitting beams of radiation that sweep across space like a lighthouse. If one of those beams points toward Earth, we can detect it as a regular pulse of radio waves. We call these pulsars. The first pulsar was discovered in the 1960s, and for a moment, people thought it might be a signal from an alien civilization because it was so regular. But it turned out to be a natural phenomenon, just a spinning neutron star. The universe is full of these remnants, old stars that have run out of fuel and collapsed into white dwarfs, neutron stars, or black holes. They're scattered throughout galaxies, invisible or nearly invisible, adding to the total mass but not contributing much light. In a way, they're the universe's way of recycling. The material from dead stars eventually gets incorporated into new stars and planets. The atoms in your body passed through several generations of stars before they ended up in you. Stars form in clouds of gas and dust called nebulae. These clouds can be enormous, hundreds of light years across, containing enough material to make thousands or even millions of stars. When a region of a nebula becomes dense enough, gravity takes over and pulls the gas inward. The cloud fragments into smaller clumps, and each clump collapses to form a star. Sometimes a clump is too small to form a star, and it becomes a brown dwarf instead, an object that's bigger than a planet but not massive enough to sustain fusion. Star formation is happening all the time, even now. There are regions in our galaxy where new stars are being born. One of the most famous is the Orion Nebula, a glowing cloud of gas visible to the naked eye in the constellation Orion. Inside that nebula, stars are forming right now, surrounded by disks of gas and dust that will eventually become planets. In a few billion years, those stars will have their own solar systems, their own planets, maybe even their own life. The process of star formation is slow and gentle, at least from a human perspective. A nebula might take millions of years to collapse and form stars, but once a star turns on, it can shine for billions of years, steadily fusing hydrogen into helium, providing light and heat to anything nearby. Planets form from the leftover material in the disk around a young star. Small particles of dust stick together, forming larger clumps. Those clumps collide and merge, growing bigger and bigger until they become planetesimals, then protoplanets, and finally full-sized planets. The process is chaotic. Collisions are common. Some objects are flung out of the system entirely. Some spiral inward and fall into the star. But eventually, things settle down and a stable solar system emerges. Our solar system has 8 planets. 4 small, rocky planets close to the Sun, Mercury, Venus, Earth, and Mars, and 4 large, gaseous planets farther out, Jupiter, Saturn, Uranus, and Neptune. Beyond Neptune, there's a region of icy objects called the Kuiper Belt, and beyond that, an even more distant region called the Oort cloud, a spherical shell of icy bodies that marks the outer edge of the Sun's gravitational influence. Each planet is different. Mercury is small and heavily cratered, with no atmosphere to speak of. Venus is about the same size as Earth, but it has a thick atmosphere of carbon dioxide that traps heat, making it the hottest planet in the solar system. Earth is the only planet we know of with liquid water on its surface and life. Mars is cold and dry now, but it may have had liquid water in the past, and there's still ice at its poles. Jupiter is the largest planet, a giant ball of gas with colorful bands of clouds and a massive storm called the Great Red Spot that's been raging for hundreds of years. Saturn is famous for its rings, which are made of countless particles of ice and rock, all orbiting the planet in a thin, flat disk. Uranus and Neptune are ice giants, with thick atmospheres and blue-green colors caused by methane in their atmospheres. Each planet has its own moons. Some are small and irregularly shaped, probably captured asteroids. Some are large and round, with their own geology and atmospheres. Jupiter's moon Europa has an icy surface with a liquid ocean underneath, kept warm by tidal heating from Jupiter's gravity. Saturn's moon Titan has a thick atmosphere and lakes of liquid methane on its surface. These moons are worlds in their own right, with their own stories. Space exploration has allowed us to visit some of these places. We've sent robotic spacecraft to every planet in the solar system. We've landed on Mars, Venus, and Titan. We've flown by Pluto and countless asteroids and comets. We've sent probes into the Sun's atmosphere and out beyond the edge of the solar system. And every mission has taught us something new about our cosmic neighborhood. A Voyager spacecraft launched in the 1970s are now in interstellar space, beyond the influence of the Sun's solar wind. They're still sending back data, faint signals from billions of kilometers away, traveling at the speed of light, taking hours to reach Earth. Those spacecraft carry golden records with sounds and images from Earth, a message to any intelligent beings who might find them someday. It's a hopeful gesture, a way of saying that we were here, that we existed, that we looked out at the universe with curiosity and wonder. Humans have walked on the moon, 12 people, all between 1969 and 1972. They explored the surface, collected samples, took photographs, and came home. The moon is the only other world humans have ever set foot on. It's close, just 3 days away by spacecraft, and yet we haven't been back in decades. Maybe we will again someday. Maybe people will live on the moon, or on Mars, or in space stations orbiting Earth. Maybe humanity will spread out beyond Earth, becoming a multi-planet species. Or maybe not. The future is uncertain.
But for now, Earth is our home. It's the only place in the universe where we know life exists, and it's a beautiful place. From space, Earth looks like a blue marble, with white clouds swirling over the oceans and brown and green continents. It's fragile, small, and precious. Everything we know, everyone we love, every human who has ever lived has lived on that small blue world. The universe is vast, but Earth is special because it's ours. It's where we evolved, where we learned to think and create and explore. It's where we look up at the night sky and wonder what's out there. And that sense of wonder is something worth holding on to. Let's talk about galaxies again, because they're endlessly interesting. Galaxies come in many shapes and sizes, but they can be roughly divided into a few categories. Spiral galaxies, like the Milky Way and Andromeda, have flat disks with spiral arms and a central bulge. Elliptical galaxies are more spherical or elongated, with no clear structure. Irregular galaxies have no defined shape at all. And there are also dwarf galaxies, which are much smaller than typical galaxies, containing only a few billion stars instead of hundreds of billions.
Spiral galaxies are often beautiful, with elegant arms that wrap around the center. Those arms are not solid structures. They're regions where stars and gas are temporarily more concentrated, creating a wave that moves through the disk. Stars drift in and out of the arms as they orbit the galaxy. The arms themselves are like traffic jams, places where the density is higher for a while before things spread out again. Elliptical galaxies tend to be older. They have less gas and dust, and not much star formation is happening in them. Most of their stars are red and cool. Spiral galaxies, on the other hand, often have active star formation in their disks, especially in the spiral arms. Young, hot blue stars light up those regions, making the arms stand out. Galaxies can interact with each other. When two galaxies pass close by, their gravitational pull can distort each other's shapes, pulling out long streams of stars and gas. Sometimes galaxies collide and merge, forming a single larger galaxy. This process takes millions of years, and even though we call it a collision, individual stars almost never hit each other. Space within a galaxy is so empty that stars pass by each other without touching. But the overall shapes of the galaxies change dramatically, and the gas clouds within them can collide, triggering bursts of new star formation. Our Milky Way is on a collision course with Andromeda. In about 4 billion years, the two galaxies will begin to merge. The process will take a long time, with multiple passes before they finally settle into a single, larger galaxy. By that time, the Sun will be nearing the end of its life, becoming a red giant. So the fate of our solar system is tied up with both the aging of the Sun and the merging of our galaxy with Andromeda. But again, this is billions of years away. It's not something to worry about. It's just part of the natural evolution of the universe. Galaxy clusters can contain hundreds or thousands of galaxies, all held together by gravity. The space between galaxies in a cluster is filled with hot gas, so hot that it emits X-rays. We can detect that gas with X-ray telescopes, revealing the invisible structure of the cluster. Galaxy clusters are the largest gravitationally bound objects in the universe. Beyond that scale, the expansion of space dominates, and structures don't stay bound together. The largest galaxy clusters are connected by filaments of gas and dark matter, forming the cosmic web. These filaments can stretch for hundreds of millions of light years, connecting one cluster to another. And in between, there are the voids, vast regions where very few galaxies exist. The voids are not completely empty. There are some galaxies there, just very few and far between. Mostly it's just space, expanding, stretching, carrying along whatever small amount of matter happens to be there. This structure, the cosmic web, is one of the most remarkable features of the universe. It's a large-scale pattern that emerges naturally from the action of gravity on matter. Small variations in density in the early universe grew over time, amplified by gravity, until they became the filaments and voids we see today. It's a self-organizing system, beautiful in its simplicity and complexity. If the listener wants to, they can like this video, but only if it feels right. There's no pressure. This is just a quiet space for rest. Let's think about cosmic horizons. The observable universe has an edge, but it's not a physical edge. It's just the farthest distance from which light has had time to reach us. Beyond that distance, light hasn't had time to travel to us yet, so we can't see it. As time goes on, that horizon expands. We can see a little farther each year as light from more distant regions reaches us. But there's a complication. The universe is expanding, and the expansion is accelerating. This means that distant galaxies are moving away from us faster and faster. Eventually, some galaxies will be moving away so fast that their light will never reach us, even if we wait forever. Those galaxies are beyond what's called the cosmic event horizon. We can see them now because their light is already on its way to us. But new light leaving those galaxies today will never reach us because the space between us and them is expanding faster than light can cross it. So the observable universe is not the same as the reachable universe. There are galaxies we can see now, but we could never travel to because they're moving away too fast. And there are galaxies beyond our horizon that we'll never see at all, no matter how long we wait. This is a strange consequence of the expansion of space. It means the universe we can interact with is limited not just by the speed of light, but also by the expansion of space itself. But it's also a reminder that the universe is much larger than what we can observe. There's more out there beyond the horizon, existing quietly, doing its own thing, completely unaware of us. Time itself might be infinite, or it might not. We don't know. The universe has a beginning, as far as we can tell, about 13.8 billion years ago. But does time itself have a beginning? That's harder to say. Our understanding of physics breaks down in the earliest moments of the universe, when everything was extremely hot and dense. We can trace things back to a fraction of a second after the beginning, but before that, we're not sure what happened. Maybe time began then. Maybe it existed before in some form we don't understand. And what about the future? Will the universe end? That depends on the expansion. If the expansion continues to accelerate, driven by dark energy, the universe will keep spreading out, becoming colder and emptier. Stars will eventually run out of fuel, galaxies will fade, black holes will evaporate through a process called Hawking radiation, though that takes an unimaginably long time. Eventually, the universe will reach a state called heat death, where everything is at the same temperature and no energy is available to do work. It will be cold, dark, and still. But that's trillions upon trillions of years in the future. For now, the universe is young and active, full of stars and galaxies, full of light and motion. There's no need to dwell on the end. It's so far away that it might as well be infinite. Some people wonder if the universe is a simulation, a kind of computer program running in some higher reality. It's an interesting idea, but it's not something we can test. If we're in a simulation and the simulation is perfect, there'd be no way to detect it from the inside. And if it's not perfect, we'd need to find glitches or inconsistencies in the laws of physics. So far, we haven't found any. The universe behaves consistently, following rules that we can measure and predict. Whether the universe is a simulation or not, it's still the universe we live in. It's still real to us. The stars are still there. The galaxies are still there, and we can still look up and wonder about them. The nature of reality is a deep question, one that philosophers and scientists have pondered for centuries. But for tonight, we can just let it be a question without needing an answer. Another question people ask is whether we're alone in the universe. Are there other intelligent beings out there on other planets, looking up at their own night skies and wondering the same thing? We don't know. We haven't found any evidence of life beyond Earth yet. But the universe is so vast, with so many stars and planets, that it seems unlikely we're the only ones. There are billions of stars in our galaxy, and many of them have planets. Some of those planets are in the habitable zone, the region around a star where conditions might be right for liquid water to exist. Water is essential for life as we know it, so planets in the habitable zone are good places to look for life. We've started searching. We've sent radio signals into space, hoping someone might hear them. We've listened for radio signals from other civilizations. We've studied planets around other stars, looking for signs of atmospheres that might contain oxygen or other gases produced by life. So far, we haven't found anything definitive. But the search is just beginning. We've only looked at a tiny fraction of the stars in our galaxy. Maybe we'll find microbial life on Mars, or in the oceans of Europa or Enceladus. Maybe we'll detect a signal from a distant civilization. Or maybe we're alone, the only conscious observers in a vast, empty universe. We don't know yet, but the question itself is worth asking, and the search is worth doing, because the answer, whatever it is, will tell us something profound about our place in the cosmos. If we are alone, it makes Earth even more precious. It means we're the only place in the universe where life has arisen, at least as far as we know. That's a heavy responsibility. It means taking care of our planet, protecting the life that exists here, because it might be the only life anywhere. If we're not alone, it means the universe is even more interesting than we thought. It means there are other beings out there, with their own thoughts, their own cultures, their own ways of seeing the universe. It means we're part of a larger community, even if we haven't met our neighbors yet. Either way, the universe is a remarkable place. It's vast, ancient, and full of wonders, and we get to be a part of it, if only for a brief moment. Stars twinkle when we look at them from Earth, but that's just an effect of our atmosphere. The air is constantly moving, and that motion bends the light from stars as it passes through. In space, stars don't twinkle. They shine steadily, constant points of light against the darkness. Astronauts who've been in space describe the stars as incredibly bright and sharp, no longer softened by the atmosphere. The view must be stunning, seeing the universe as it really is, without the filtering effect of air. Someday, maybe more people will get to see that view. Space tourism is just beginning, and as technology improves, it might become more common for ordinary people to visit space, to see Earth from above, to see the stars without the atmosphere in the way. But even from the ground, with the atmosphere blurring things slightly, the night sky is beautiful. If you're somewhere dark, away from city lights, you can see the Milky Way stretching across the sky, a faint band of light made up of billions of stars. You can see planets moving slowly against the background of stars. You can see satellites reflecting sunlight as they orbit Earth. You can see meteors, tiny pieces of rock burning up in the atmosphere, leaving brief streaks of light. The night sky connects us to the universe. It reminds us that we're not separate from the cosmos, but part of it. Every atom in your body was forged in a star. Every breath you take contains atoms that were once part of other living things, other planets, other stars. You're made of the universe, and the universe is made of you. There's a concept in astronomy called deep time. It's the idea of thinking in terms of millions and billions of years, scales of time so long that they're hard to comprehend. Human lifetimes are measured in decades. Civilizations rise and fall over centuries or millennia. But the universe operates on timescales that dwarf all of that. A mountain might take millions of years to erode away. A continent might take tens of millions of years to drift across the planet's surface. A galaxy might take hundreds of millions of years to complete one rotation. These processes are happening, but they're so slow that we can't perceive them directly. We can only see the evidence they leave behind. Deep time gives us perspective. It reminds us that the universe is patient. It doesn't rush. It unfolds at its own pace, indifferent to our human sense of urgency. And there's something calming about that. We can let go of our need to control everything, to understand everything right now. We can accept that some things take time, and that's okay. The concept of infinity is also worth thinking about. Is the universe infinite in size? We don't know. It might be. Or it might be finite but unbounded, like the surface of a sphere. If you travel far enough in one direction, you might end up back where you started without ever hitting an edge. It's hard to imagine, but mathematically, it's possible. Is time infinite? That's also uncertain. It might extend forever into the future, or there might be an end, some point where time itself ceases to have meaning. And what about the past? Did time have a beginning, or did it always exist? These are questions that might not have answers, or at least not answers we can understand with our current knowledge.
But infinity, whether it exists or not, is a useful concept. It helps us think about limits, about what it means for something to go on forever. And it reminds us that even though we can learn a lot about the universe, there might always be things beyond our reach, things we can never fully know. Mathematics is the language we use to describe the universe. Numbers, equations, geometry, all of these tools help us understand how things work. The orbits of planets can be described with equations. The bending of light by gravity can be calculated. The expansion of the universe can be measured. Mathematics gives us a way to make precise predictions, to test our theories, to communicate ideas clearly. But mathematics is also beautiful in its own right. There's elegance in a simple equation that describes a complex phenomenon. There's satisfaction in solving a problem, in seeing how different pieces fit together. And there's a sense of wonder in discovering that the universe follows mathematical rules, that the language of numbers and equations is somehow built into the fabric of reality. Physicists talk about the unreasonable effectiveness of mathematics. Why should abstract mathematical concepts invented by human minds correspond so well with the real world? Why should the universe be mathematical at all? It's a mystery, one that we might never fully understand. But it's also a gift, because it means we can use mathematics to explore the universe, to predict what will happen, to understand the deep structure of reality. Patterns occur everywhere in nature. The spiral shape of galaxies, the hexagonal structure of snowflakes, the branching patterns of rivers and trees. These patterns emerge from simple rules, repeated over and over. A spiral galaxy forms because of the way gravity and rotation interact. A snowflake forms because of the way water molecules bond together as they freeze. A river branches because water follows the path of least resistance. The universe is full of these emergent patterns, complex structures arising from simple underlying laws. And that's part of what makes the universe so fascinating. You don't need complicated rules to get complexity. You just need a few simple principles acting over and over, and the complexity emerges naturally. Fractals are a good example of this. A fractal is a pattern that is the same pattern again, smaller. Zoom in more and you see it again. Coastlines are fractal-like. Mountains are fractal-like. The distribution of galaxies in the universe has fractal properties. It's a recurring theme in nature, this idea of self-similarity, of patterns within patterns. Light is fascinating in its own right. It's both a wave and a particle, depending on how you look at it. When light travels through space, it behaves like a wave, with peaks and troughs, a certain wavelength and frequency. But when light interacts with matter, it behaves like a stream of particles called photons. Each photon carries a tiny amount of energy, and when it hits something, it can transfer that energy. This dual nature of light, wave and particle at the same time, was one of the big puzzles of early 20th century physics. It led to the development of quantum mechanics, a new way of thinking about the universe at very small scales. Quantum mechanics is strange. It says that particles don't have definite positions or velocities until you measure them. Before measurement, they exist in a kind of fuzzy state, a superposition of possibilities. Only when you observe them do they collapse into a definite state. This sounds bizarre, and it is, but it's also how the universe works, at least at small scales. Electrons in atoms exist in these fuzzy quantum states. Light can be in a superposition of different paths, and this quantum behavior underlies all of chemistry and biology. The way atoms bond together, the way molecules interact, the way enzymes catalyze reactions in your body, all of it depends on quantum mechanics. But at large scales, quantum effects average out, and the universe behaves more classically. Planets orbit in definite paths. Light travels in straight lines or curves around massive objects. Quantum mechanics is still there, in the background, but it doesn't show up in obvious ways. The universe is layered, with different rules applying at different scales. Energy cannot be created or destroyed. That's one of the fundamental laws of physics, called the conservation of energy. Energy can change forms. It can be kinetic energy, the energy of motion. It can be potential energy, stored energy waiting to be released. It can be heat, light, chemical energy, nuclear energy. But the total amount of energy in a closed system never changes. This law applies to the entire universe. All the energy that exists now has always existed, just in different forms. The light from stars is energy that was locked up in the nuclei of atoms, released through fusion. The warmth you feel from the sun is energy that traveled across space as light, then absorbed by your skin and converted to heat. The food you eat contains chemical energy that was stored by plants through photosynthesis, capturing light from the sun and converting it to sugars. Energy flows through the universe, changing forms, moving from place to place, but never disappearing. It's a kind of constancy, a conservation law that applies everywhere at all times. And there's something comforting about that. The universe follows rules. Energy is conserved. Momentum is conserved. Certain quantities remain constant even as everything else changes. The speed of light is constant too. No matter how fast you're moving, no matter where you are, light always travels at the same speed relative to you. If you're on a train moving forward and you throw a ball forward, the ball moves faster relative to the ground than it does relative to you. But light doesn't work that way. If you're on a train moving at half the speed of light and you shine a flashlight forward, that light doesn't travel at 1.5 times the speed of light. It still travels at exactly the speed of light, both relative to you and to someone standing still. This constancy of the speed of light is what led Einstein to develop special relativity. If the speed of light is constant for everyone, then time and space must be flexible, adjusting themselves to keep the speed of light the same. It's a strange idea, but it's been tested countless times, and it's always confirmed. The speed of light is a fundamental constant of the universe, woven into the structure of space-time itself. There are other fundamental constants too: the strength of gravity, the charge of an electron, the mass of a proton. These values seem arbitrary, We don't know why they have the values they do. But if they were even slightly different, the universe would be a very different place. Stars might not form, atoms might not be stable, life might not be possible. This has led some people to wonder if our universe is special, fine-tuned for life, or maybe there are many universes, each with different values for these constants, and we happen to live in one where the constants allow for stars, planets, and life. That's the multiverse idea, and it's speculative. We can't observe other universes if they exist, but it's an interesting thought. Maybe the universe we see is just one of many, each with its own laws and constants. But whether there are other universes or not, this one is the only one we can observe, and it's a remarkable place. The constants happen to have values that allow for complexity, for structure, for stars and galaxies and planets, and life. We're lucky, in a sense, to exist in a universe where such things are possible.
Gravity is the weakest of the fundamental forces, but it's the one that shapes the large-scale structure of the universe. On small scales, electromagnetism is much stronger. The electric force between two protons is about 1,000,000 trillion times stronger than the gravitational force between them. But gravity has one advantage. It's always attractive, and it acts on everything. Electromagnetism can be attractive or repulsive, and opposite charges cancel out. But gravity only pulls, never pushes, and all mass contributes. So over large distances, gravity dominates. It pulls gas into stars. It holds planets in orbit. It binds galaxies together. It shapes the cosmic web. Gravity is the architect of the universe, working slowly, patiently, over billions of years to create the structures we see. The other fundamental forces operate at smaller scales. The strong nuclear force holds atomic nuclei together, binding protons and neutrons. The weak nuclear force is responsible for certain kinds of radioactive decay. Electromagnetism governs how charged particles interact, and it's responsible for chemistry, for the way atoms bond together to form molecules. These four fundamental forces, gravity, electromagnetism, the strong force, and the weak force, are all we need to explain everything we observe in the universe. They're the fundamental interactions, the basic ways that matter and energy can affect each other. Everything else is built from these. Scientists have been trying to unify these forces, to find a single theory that explains all of them. Electromagnetism and the weak force have already been unified into something called the electroweak force. The strong force has been incorporated into the same framework, creating what's called the standard model of particle physics. But gravity remains separate. It's described by general relativity, a very different kind of theory. Finding a theory of quantum gravity, a way to describe gravity using the same language as the other forces, is one of the biggest challenges in physics. String theory and loop quantum gravity are two approaches, but neither has been confirmed by experiment. It's an ongoing effort, one that might take decades or centuries to resolve. Or maybe it's a problem that has no solution, at least not one we can understand. But even without a complete theory of everything, we've learned an enormous amount about the universe. We understand how stars work, how galaxies form, how the universe expands. We can predict the motion of planets with incredible accuracy. We can look back in time to see the universe as it was billions of years ago. We can peer into the hearts of atoms and observe the particles that make up matter. Science is a process of learning, of asking questions and seeking answers. It's not about having all the answers right away. It's about making progress, bit by bit, building on what we've learned before. And there's always more to learn. The universe is vast and complex, and every answer raises new questions. The atoms in your body are ancient. The hydrogen atoms were formed in the first few minutes after the universe began. The carbon, oxygen, and nitrogen atoms were formed in stars that lived and died billions of years ago.
Those atoms have been recycled countless times, passing through stars, through space, through planets, through living things. Some of the atoms in your body might have been part of a dinosaur once. Some might have been part of a tree, or a fish, or a bacterium. Some might have drifted through space for billions of years before ending up on Earth. You're a temporary collection of ancient atoms, borrowed from the universe for a brief time, and eventually they'll be returned, recycled again into new forms. This cycle of matter is one of the ways the universe renews itself. Nothing is truly lost. Everything is transformed. The atoms that make up a star today might be part of a planet tomorrow. The atoms that make up a planet might someday be part of another star. Matter flows through the universe, changing forms but always conserved. Water is a good example of this. The water on Earth has been here for billions of years, cycling through the oceans, the atmosphere, the land, and living things. The water you drink today might have fallen as rain on a forest 1,000 years ago. It might have been part of a river, or an iceberg, or a cloud. It's the same water, endlessly recycled. The same is true for all matter. The universe is a closed system, at least as far as we can tell. Nothing new is being added. Nothing is being taken away. It's all just rearranging itself over and over, forming new structures, new patterns, new combinations. Clouds are beautiful. They form when water vapor in the atmosphere cools and condenses into tiny droplets or ice crystals. Those droplets or crystals are so small that they float in the air, carried by the wind. When enough of them gather together, they form a visible cloud. Clouds can take many shapes, from thin, wispy cirrus clouds high in the atmosphere to thick, towering cumulonimbus clouds that produce thunderstorms. Clouds are always changing, forming and dissolving, drifting across the sky. They're temporary structures, held together by the balance between gravity pulling the droplets down and air currents pushing them up. Eventually, the droplets grow large enough that gravity wins, and they fall as rain or snow. The same process happens on other planets. Venus has thick clouds of sulfuric acid. Mars has thin clouds of water ice and carbon dioxide. Jupiter and Saturn have clouds made of ammonia and other compounds. Clouds are a common feature of planetary atmospheres, forming wherever there's gas and temperature differences. On Earth, clouds play an important role in the climate. They reflect sunlight back into space, cooling the planet. But they also trap heat radiated from the surface, warming the planet. The balance between these two effects determines whether clouds have a net cooling or warming effect. It's complicated, and it's one of the uncertainties in climate science. Weather is chaotic. Small changes in initial conditions can lead to very different outcomes. This is sometimes called the butterfly effect, the idea that a butterfly flapping its wings in one part of the world could, in theory, lead to a tornado in another part of the world weeks later. It's not that the butterfly causes the tornado directly, but that the atmosphere is so sensitive to small changes that even tiny disturbances can grow into large effects. This makes long-term weather prediction very difficult. We can forecast the weather a few days in advance with reasonable accuracy, but beyond that, the uncertainty grows rapidly. Climate, on the other hand, is more predictable. Climate is the average weather over long periods of time, and while individual weather events are chaotic, the overall patterns are more stable. The universe is full of chaotic systems, turbulent flows like the swirling patterns in Jupiter's atmosphere, the orbits of asteroids, which can be influenced by small gravitational perturbations and sent off in new directions. Even the formation of galaxies involves chaotic processes, with gas and dark matter interacting in complex ways. But despite all this chaos, there's also order. Patterns emerge, structures form. The universe is both orderly and chaotic, both predictable and surprising, and that's part of what makes it so interesting. The Moon is Earth's only natural satellite. It's about a quarter the size of Earth, which is unusually large for a moon relative to its planet. Most moons are much smaller compared to their planets. The leading theory for how the moon formed is that a Mars-sized object collided with Earth early in its history, and the debris from that collision coalesced to form the moon. The moon has a significant effect on Earth. Its gravity pulls on Earth's oceans, creating tides. High tide occurs when the moon is overhead and also when it's on the opposite side of Earth, because the moon pulls on the Earth itself, not just the water. Low tide occurs in between. The sun also contributes to tides, but the moon's effect is stronger because it's closer. Tides have shaped life on Earth. Many organisms have adapted to the rhythm of the tides, and tidal zones are rich ecosystems where land and sea meet. Tides also slow Earth's rotation very gradually. The friction between the tides and the ocean floor dissipates energy, and that energy comes from Earth's rotation. So Earth is spinning more slowly now than it did in the past, and the days are gradually getting longer. The effect is tiny, just a few milliseconds per century, but over billions of years, it adds up. The moon is also slowly moving away from Earth. As Earth's rotation slows, angular momentum is transferred to the moon, causing its orbit to expand. The moon is currently moving away at about 4 centimeters per year. Eventually, billions of years from now, the moon will be so far away that it will no longer cause significant tides, and Earth's rotation will have slowed to the point where one side always faces the moon, just as one side of the moon always faces Earth now. The moon's surface is covered in craters, the result of billions of years of impacts from asteroids and comets. Unlike Earth, the moon has no atmosphere and no geological activity to erase those craters, so they accumulate over time. The dark patches on the moon, called maria, are ancient lava flows that filled in large impact basins. They're made of basalt, a dark volcanic rock. Humans have left footprints on the moon, and those footprints will remain for millions of years. There's no wind or water to erase them. The only things that will eventually disturb them are micrometeorites, tiny grains of dust hitting the surface at high speed. But that's a slow process. The moon is a quiet place, almost perfectly still. Asteroids are rocky or metallic objects that orbit the sun, most of them in a region between Mars and Jupiter called the asteroid belt. They're remnants from the formation of the solar system, material that never coalesced into a planet. There are millions of asteroids, ranging in size from a few meters to hundreds of kilometers across. The largest asteroid, Ceres, is nearly 900 kilometers in diameter. It's big enough to be round, pulled into a spherical shape by its own gravity. Ceres is actually classified as a dwarf planet now, a category that also includes Pluto and several other objects in the outer solar system. Most asteroids are much smaller, irregularly shaped chunks of rock and metal. Some are solid, some are loose piles of rubble held together by their own weak gravity. Some asteroids have moons of their own, smaller objects orbiting them. Occasionally, an asteroid's orbit is perturbed by gravitational interactions with planets, and it can end up on a path that crosses Earth's orbit. These are called near-Earth asteroids, and some of them pose a potential impact threat. Most are small and would burn up in the atmosphere if they hit Earth, but larger asteroids could cause significant damage. Earth has been hit by large asteroids in the past. The most famous impact was 66 million years ago, when an asteroid about 10 kilometers across struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, creating a massive crater and throwing dust and debris into the atmosphere. The dust blocked sunlight, causing global cooling, and many species went extinct, including most of the dinosaurs. But impacts of that size are rare. They happen, on average, every 100 million years or so. Smaller impacts are more common. Larger impacts are rarer. Astronomers are working to identify and track all the near-Earth asteroids that could pose a threat, so that if one is found on a collision course with Earth, we might have time to do something about it. Comets are similar to asteroids, but they're made of ice and rock rather than just rock and metal.
They come from the outer reaches of the solar system, from the Kuiper Belt or the Oort cloud. When a comet's orbit brings it close to the sun, the ice begins to sublimate, turning directly from solid to gas. This creates a glowing coma around the comet's nucleus, and sometimes a long tail that points away from the sun, pushed by the solar wind. Comets are beautiful, but they're also messengers from the early solar system. The ice in comets contains water and organic molecules, and it's possible that comets delivered some of Earth's water and organic material early in its history. Earth might owe some of its oceans, and perhaps even the ingredients for life, to comet impacts billions of years ago. Some comets have highly elliptical orbits, taking them far out into the solar system and then back in close to the sun. Halley's Comet is a famous example. It returns to the inner solar system about 76 years, and it's been observed and recorded by humans for thousands of years. The last time it passed close to Earth was in 1986, and it will return in 2061. The solar wind is a stream of charged particles, mostly protons and electrons, flowing out from the sun. It travels through the solar system at hundreds of kilometers per second, carrying energy and magnetic fields. When the solar wind reaches Earth, it interacts with Earth's magnetic field, creating beautiful displays called auroras near the poles. Auroras occur when charged particles from the solar wind get trapped by Earth's magnetic field and funnel down toward the poles. As they collide with atoms in the upper atmosphere, they excite those atoms, causing them to emit light. Oxygen atoms emit green or red light, depending on altitude. Nitrogen atoms emit blue or purple light. The result is a shimmering curtain of color in the night sky, dancing and shifting. Auroras are most common near the poles, in regions called the auroral ovals. But during strong solar storms, when the sun releases a particularly intense burst of particles, auroras can be seen at lower latitudes. They're one of the most beautiful natural phenomena on Earth, a visible connection between Earth and the sun. Other planets have auroras too. Jupiter and Saturn have intense auroras near their poles, much brighter than Earth's, because those planets have stronger magnetic fields and more energetic particles. Even Mars has weak auroras, though it lacks a global magnetic field like Earth's. The sun itself is constantly changing. Its surface is covered in features like sunspots, dark regions where the magnetic field is particularly strong and the temperature is slightly cooler. The number of sunspots varies over an 11-year cycle, with periods of high activity called solar maximum and periods of low activity called solar minimum. During solar maximum, the sun is more active, with more sunspots, more solar flares, and more coronal mass ejections. Solar flares are sudden bursts of energy released when magnetic field lines on the sun reconnect. Coronal mass ejections are huge clouds of plasma ejected from the sun's outer atmosphere. Both can send charged particles hurtling toward Earth, potentially disrupting satellites, communication systems, and power grids. But the sun is generally stable. It's been shining steadily for billions of years, and it will continue to do so for billions more. The variations in its activity are small compared to its overall output. The sun is a reliable source of energy, and life on Earth depends on that reliability. Photosynthesis is the process by which plants, algae, and some bacteria capture light from the sun and convert it to chemical energy. They use that energy to convert carbon dioxide and water into sugars, releasing oxygen as a byproduct. This process is the foundation of most life on Earth. Plants use the sugars for energy and growth. Animals eat plants or eat other animals that eat plants, and in this way, the energy from sunlight flows through the entire ecosystem. Photosynthesis also produces the oxygen in Earth's atmosphere. Before photosynthetic organisms evolved, Earth's atmosphere had very little oxygen. But as photosynthesis became widespread, oxygen levels increased, eventually reaching the levels we have today. This allowed oxygen-breathing organisms to evolve, including eventually complex animals like us. The oxygen we breathe, the food we eat, the energy we use, almost all of it can be traced back to sunlight. The sun powers life on Earth, not just by providing warmth and light, but by driving the processes that create the energy and molecules living things need. Even fossil fuels, coal, oil, and natural gas, are ultimately derived from ancient sunlight. They're the remains of plants and other organisms that lived millions of years ago, capturing sunlight through photosynthesis. Over time, those remains were buried and transformed by heat and pressure into the fuels we use today. When we burn fossil fuels, we're releasing energy that was captured from the sun millions of years ago. Renewable energy sources like solar and wind power are more direct ways of capturing energy from the sun. Solar panels convert sunlight directly to electricity. Wind turbines capture the motion of air, and that motion is driven by temperature differences caused by uneven heating of Earth's surface by the sun. Even hydroelectric power is indirectly solar, because the water cycle that fills rivers and lakes is powered by sunlight evaporating water from the oceans. The sun is the ultimate source of almost all the energy we use, and the sun's energy comes from fusion, from the conversion of mass into energy deep in its core. Einstein's famous equation, E equals mc squared, describes this relationship. A small amount of mass multiplied by the speed of light squared equals a huge amount of energy. That's why fusion is so powerful. The mass of the atoms consumed in the sun's core is converted into energy, and that energy radiates outward, eventually reaching Earth. Humanity has tried to replicate fusion on Earth to create a clean, virtually limitless source of energy. Fusion reactors are still experimental, and making them practical is a difficult challenge, but progress is being made. Someday, we might be able to power our civilization with fusion, just as the sun powers itself. The universe has given us everything we need to exist: the atoms in our bodies, the energy that powers life, the planet we live on, the star that warms us. We're part of a vast, interconnected system, and everything we are and everything we have comes from the universe itself. There's a certain poetry to that. We're children of the cosmos, made of stardust, shaped by billions of years of evolution, standing on a small planet, looking out at the universe and trying to understand it. And in some small way, through us, the universe is becoming aware of itself. We're the universe looking back at itself, thinking, wondering, exploring. That's a profound thought, but it doesn't need to be overwhelming. It can just be a quiet realization, something to hold gently as you drift off to sleep. You're part of something vast and ancient and beautiful. You're connected to the stars, to the galaxies, to the very fabric of space-time. And for tonight, that's enough. You don't need to understand everything. You don't need to remember any of this. You can just let it wash over you, a soft reminder that you're part of the universe, and the universe is unfolding exactly as it should. Rest now. Let your thoughts settle. Let your body relax. The universe will still be here tomorrow, vast and patient, waiting to be explored. But for now, just rest. Everything is okay. Everything is calm.
If you found this peaceful, you're welcome to explore more like it anytime, but there's no rush. Sleep well.